This video is sponsored by Squarespace, an all-in-one website builder to create professional websites with ease. The escapement is the most important part of a watch. Fundamentally, it is the assembly that generates periodic pulses that we can use to keep time. This is, in fact, the essence of the measurement of time, and in the case of an atomic clock, we measure the number of oscillations of a cesium atom. A quartz watch, we use an electronic oscillator, and a mechanical watch uses a balance wheel. In this video, Alastair and I work together to make a chronometer escapement mechanism, beginning with the bridge that holds the main bearing and supports the balance wheel. Throughout the video, we use traditional watchmaking techniques, many of which use simple hand tools. Here, I'm cutting the bridge from brass plate using a piercing saw, which I then file to shape. We opted to scale this mechanism by approximately 2 to 3 times the size of what you would expect to see in a watch, to make it easier for you to see how it works. Nevertheless, some of the components are still tiny, such as this ball bearing, which I'll press into the bridge to support the balance wheel. This bearing has a bore of 1mm and an OD of 3. In a mechanical watch, instead of ball bearings, ruby jewels are used instead. This is a great way of generating a low friction, hard wearing bearing at the scale of a watch, which is just not possible with ball bearings. In fact, usually a good quality watch will have other jeweled pivots too throughout the whole movement. The number of jewels used in a movement is often marked on the front of a watch. Whether it is a jewel or a bearing, a press fit is a simple method of holding the bearing in place. Here I use a hand reamer to enlarge the drilled hole, but because the end of the reamer is very slightly tapered, I can control the depth of my reaming to determine the fit of the bearing. I measure this using pin gauges. The bridge is supported on pillars which locate in holes at each end, so I drill these now. To finish filing the bridge, I machine a button to act as a filing guide. Traditionally, these are made from hardened steel, which makes for a foolproof system, but will dull files, so I opt to make these from brass. To finish the edges, I use a fine escapement file. Moving side to side like this is called draw filing, which creates a uniform grain. I machine the pillars from silver steel. The first side I'm machining here will have a male thread, and the other side will have a female thread and a spigot to locate the bridge. It's really important that the bridge is accurately located. This will help to minimise friction in the bearings and ensure the components attached to the balance staff interface with each other properly. I'll show you specifically later on. Normally I use a cutting liquid to lubricate the die when cutting small threads. Here, instead, I experiment with a paste. The surface finish leaves something to be desired, so I'll go back to the cutting liquid in the future. I face the thread to length and apply a small undercut so I can tighten the pillar all the way into the main plate. To ensure the bearings are axially aligned, I take the time to carefully machine the length of each pillar to within around 5 microns of their nominal size. The end can then be drilled and tapped to accept the bridge screws. I decide to keep the bridge pillars uniform cylinders. In a watch, these are usually embellished by being thinned in the middle. In the case of a tourbillon watch, it would be beneficial to thin them to reduce their weight and therefore the inertia of the tourbillon carriage. Now I begin work on the main plate. Using traditional techniques, the main plate is revisited throughout the entire watchmaking process. Gradually, more and more holes are marked out and drilled as the other components are machined. Using modern methods, the main plate is made in one go according to measurement in a CNC machine. Here, I use the bridge as a template. This ensures that everything is in correct alignment, even if my initial marking out was inaccurate. From this point, every time I assemble the bridge and main plate, I will make sure to maintain the same orientation. To make sure I don't mar the surface of the pillars, I use brass-faced pliers to screw the pillars into the plate. Before we get cracking on the balance wheel, here's a quick word from our sponsor.
Thanks again to Squarespace for sponsoring this video. One of my favourite Squarespace features is their courses tool. Sharing your unique expertise online can be a great way to generate passive income, and Squarespace's professional templates make this super easy to set up. Courses on Squarespace use the same intuitive fluid engine tools as the rest of your Squarespace website, so you can seamlessly add professional design features like scrolling text or video backgrounds. Squarespace also lets you schedule classes for future release and select whatever pricing or subscription works for you. You can even augment your content by selling memberships, services, and physical products on the same website. To try Squarespace for yourself, head to squarespace.com for a free trial, and when you're ready to launch, visit squarespace.com/Chronova Engineering to get a 10% discount on your first website or domain.
Now let's move over to Alastair's workshop where he begins work on the balance wheel. The balance wheel forms the oscillator of the watch. This component is vital both in its function but also in its aesthetics, as the eye is drawn to this part of the watch first. Balance wheels come in many shapes and sizes, and some of these design differences are as a result of artistic expression, but many of them also serve a purpose, such as temperature compensation. In this case, Alastair opts for the recessed screw balance, which allows easy poising by adjusting the screws in the rim. This version is not temperature compensated, but considering the purpose of this is to demonstrate the principle, it does not need to be an accurate timekeeper. Alastair begins by roughing out the disc shape in the lathe before parting it off and mounting it back in the machine for marking out the spokes. The spokes are then cut and filed to shape. These aluminium vice jaws are specially designed to guide the file and can be easily rejuvenated in the milling machine once they become worn with use. A spacer the same thickness as the balance wheel is held in place at the bottom of the vice jaws to ensure parallel clamping. The recesses for the screws are cut out with a piercing saw, and the wheel is ready for radial drilling on the milling machine mounted to the dividing head. Alastair finishes shaping the balance wheel using a piercing saw and files. Handwork like this is time consuming but hugely rewarding. Using relatively simple tools, complex shapes can be formed. Personally, I am a huge advocate for modern technology such as CNC machines and 3D printers, and I've used them regularly, but this handwork, whilst perhaps not commercially viable anymore, is a hugely satisfying pastime. For those of you who might want to try metalwork, but don't necessarily want to jump straight into machining, you can go a long way with a small selection of saws and files. It's now back over to me to finish the balance wheel off. I machine the screws on the watchmaker's lathe due to their small size. These are M1 screws, but have a long head to add extra mass. The purpose of these screws is twofold. Their first use is to adjust poise. This is the term watchmakers use to describe balancing, or ensuring an even distribution of weight around the balance wheel. Their second function is to subtly adjust the inertia of the wheel, which is a sensitive method of adjusting the rate. As the screws are wound outwards, the wheel inertia increases and the balance wheel slows down. And inversely, the balance wheel oscillations speed up when the screws are wound inwards. Here I use a broach to open the holes in the balance wheel periphery to the tapping drill size. These broaches are actually slightly tapered, but over this very short length the hole can be assumed parallel. I deburr the hole and tap by hand using a handheld chuck. Once all the holes are tapped, I clean the wheel in acetone and give it a touch up with escapement files and emery paper. This is a good time to make the balance staff. In a typical watch, this is one of the most difficult parts to make because the pivots are typically machined to around 0.1mm in diameter. Additionally, extra care has to be taken for all aspects to be perfectly concentric, so it should be finished between centres. However, this is a demonstration model and I'm using ball bearings, so this particular component is actually trivial to make. Note, this is bad practice, but here I rely on the accuracy of my collets and machine the ends to around 3 microns oversize, where I can burnish down till the bearing is a light press fit. At this point I can't fit the balance wheel directly to the staff, so I machine a brass ring which I can attach to the balance wheel to interface with the balance staff. Again, we differ from a traditional watch here, where we would normally machine this part into the balance staff. In larger engineering applications, there are several ways we can attach something to a shaft. Some examples that come to mind are shrink fitting, grub screws, welding, brazing or gluing. In watchmaking though, we almost exclusively use a staking process. I demonstrate this here, where I simply use a punch to deform the metal in such a way as to accurately rivet the components together. The staking tool holds the stake or punch in an upright position to ensure everything is accurately fixed together without asymmetry. The balance wheel pivots are the most important pivots in the mechanism. The less friction here, the better. Here you can see the balance wheel is extremely free running, which is exactly what I'm after. Going back to Alastair's workshop, he has begun to work on the escape wheel. The escape wheel can be made in a similar way to any gear, but it has a unique tooth profile that can't be machined using an off-the-shelf cutter. So Alastair first makes a custom-shaped cutter using a grinder. The teeth of the escape wheel engage with two other components, and each of these components serve a different purpose. One component is the locking stone that we come onto later, but this holds the escape wheel in a fixed position for most of the balance oscillation. When the escape wheel is not held by the locking stone, it provides an impulse of energy into the balance wheel to keep it oscillating. It achieves this by engaging with a surface fixed to the balance staff called an impulse pallet. I will explain this in more detail later in the video. Here, Alastair sets up to drill 4 holes in the end of an aluminium rod. The end of the rod is parted off in the lathe to produce a washer, and the holes remaining in the rod are tapped. These two components will create the arbor to which the escape wheel blank can be mounted. The blank will be sandwiched between the arbor face and the washer to fully support the blank when the teeth are being cut. Alastair roughly marks and cuts out the escape wheel blank from brass sheet. Note at this point the shape can be very rough because he will machine it to the final profile in the lathe. Likewise, the position of the 4 holes do not need to be accurate. The blank is mounted in the lathe and is machined circular but still oversized. The blank is then removed to cut and file the spokes before mounting the wheel back in the lathe. Normally we would shape the spokes after cutting the teeth, but in this case, once formed, the teeth will be very thin and fragile. A bearing mounted in a tool post can be used to bring the blank back concentric. This will ensure that once finished, the spokes will be concentric to the teeth. Normally, a dividing head will use a plate with holes and a plunger. This can be fiddly to use, so Alastair instead uses a graduated dial on his dividing head to index the workpiece round as the teeth are cut with the fly cutter he made earlier. It's back over to my workshop where I work on mounting the escape wheel to its shaft. This is done in a similar way to the balance wheel, although later I opt to fix it to the shaft with a small radial screw to allow easy assembly and disassembly of the mechanism. As I mentioned earlier, one of the purposes of the escape wheel is to provide an impulse to the balance wheel, which it does through the impulse roller. For the purposes of this model, I make the impulse roller from brass, although in a watch the impulse face would usually be jewelled or at least made from hardened steel. I mount the roller and escape wheel on a depthing tool. This allows me to adjust the separation of the two components until I'm happy with their engagement. I can then use the depthing tool itself to transfer the centre separation straight onto the main plate. The impulse roller can now be staked onto the balance staff. At this point we need to consider how the escape wheel is going to be mounted. I choose to use a potence, which can be made by recessing a bar of steel using the watchmaker's faceplate. A question I am sometimes asked is, how do I design? The truth is, it varies from project to project. Sometimes Hazel will work with me to produce a detailed CAD model. At the other end of the spectrum, sometimes I just imagine what I want and make up the dimensions as I go along. Alastair usually makes a rough sketch in his lab book before starting to manufacture, but he is more organised than me. In this case, I began with a rough scale drawing, but nevertheless a lot of this work is still improvised. For instance, at this point I don't really know how deep to make the recess, because it's dependent on other parts of the mechanism. So I opt to make it too shallow to work with this handy offcut, and machine spacers later on to bring it to the correct height. The chronometer, or detent escapement, was invented in the 1700s and is particularly interesting because of its high accuracy. The design is based around the detent, which is unique to this escapement. It is a long, slender component which contains the locking stone. This locking stone holds the escape wheel in position during the supplementary arc of the balance wheel. There are two main variations of this escapement, the pivoted detent or the spring detent. Here I make the spring detent. The detent is notoriously difficult to make because it is small, but it needs to be made accurately for the escapement to work. There are some geometrical challenges, such as the spring, which is hand filed. It is partially because of the fragility of this component that this escapement was superseded by the lever escapement, which is what you would normally find in a mechanical watch today. However, you can still buy a watch with this escapement, but they aren't cheap. Here I'm drilling a hole to bolt the detent to the main plate, but as its position is critical, it's also good practice to pin it in place, so I mark and drill the hole for the pin too. I proceed with the rest of the detent with hand files. The detent requires an additional spring to be bolted onto the side. In one direction, the unlocking pallet will simply lift this additional spring from the arm of the detent, whereas in the other direction, the spring filed into the detent will be overcome and the gear train and escape wheel will be unlocked to impulse the balance wheel. Here I work on drilling and tapping the detent for this bolt. After hardening, the detent needs cleaning up, but while the metal was in its soft state, I filed the spring reasonably thin. Therefore, in its current glass hard state, the spring is very fragile. But before tempering, I need a clean surface to observe a colour change as I heat it. I very carefully clean up the spring area just enough so I can observe a colour change and temper it to a blue. I now need to work on thinning the spring with a file until it is thinner than a piece of paper. I work on a cork and clean up the rest of the detent as I proceed. I apply some beeswax to the surface of the cork, which provides a grippy surface. The beeswax holds the detent in position as I gently file the detent thinner and thinner. As the spring approaches its final thickness, the workpiece becomes very fragile and I have to handle it carefully. I cut the extra spring from brass shim and bend it to shape with tweezers. Later I opted to use a thinner shim because the thinner the shim, the less energy is lost in the escapement. The same logic can be applied to the main detent spring, but it can't be made too thin because the spring could deform under the pressure applied from the escape wheel. I temporarily clamp the detent to the main plate and play around with its position until I'm happy with how it engages with the escape wheel and the unlocking roller before I bolt it to the main plate permanently. I made the unlocking roller off camera, but it is similar to the impulse roller you saw me make earlier. Alastair works on machining the pinion. I will later stake this pinion to the same shaft as the escape wheel, so it is this pinion that will engage with the wheel, which will provide the torque to maintain the escapement. Again, we differ slightly from a traditional watch here, where the pinion would normally be staked directly to the escape wheel. In our case, we opted to move the pinion away from the escape wheel and onto the back of the main plate to make the rest of the mechanism more visible. Typically, a watch is driven by a mainspring. This spring is wound periodically to maintain power to the escapement. Instead though, we opted to drive the escapement with a weight, which is much simpler to manufacture. The weight-driven approach is normally used for clocks, which do not need to be portable. In fact, a weight is more accurate than driving a gear train with a spring because the force does not vary. Here, Alastair makes the barrel, which I will later hang the weight off. The barrel is bolted to the drive wheel, which Alastair made off camera. He then mounts the pinion and drive wheel on a depthing tool. This is a different type of depthing tool to the one I used earlier, and instead of transferring the dimensions straight from the depthing tool onto the main plate, he instead measures the separation using gauge blocks and a micrometer. I can then remotely drill the holes in the correct position based on measurement back in my workshop. Before we begin with assembly, let's make one more component. This part is the hairspring collet that allows us to attach the hairspring to the balance staff. The hairspring provides the restoring force to the balance wheel to allow it to oscillate, much like gravity does for a pendulum. The hairspring is a fascinating component, and in modern watches a huge amount of science goes into the hairspring design and materials. I'm sure this will be a topic for a future video, but for this project I'm not trying to make an accurate timekeeper, so the hairspring doesn't need to be perfect. These watch hairsprings are too small though, so I choose to modify a watch mainspring instead. The hairspring fits in the off-centre hole, where I will pin it in place with a tapered pin. I initially drill the off-centre hole when the bar stock is a larger diameter, and then machine it down to size after the hole is drilled, to reduce sideways deflection of the centre drill. The hairspring collet is slit to allow easy fitting and removal. Rather than leaving the main plate a boring rectangle, I choose to use the piercing saw and files to shape it into something more interesting. Now it's ready for assembly. I begin with mounting the escape wheel potence. I didn't pin this component, so first I align it by using the escape wheel shaft inserted through the bearing in the potence and main plate. I made this next component off camera, and it's simply an adjustable stop to control the locking position of the detent. I fit this into the main plate next. The detent, complete with its upgraded spring and locking stone, which I filed from silver steel, is then bolted in place. Normally the locking stone would be a jewel, hence the name. I slide the escape wheel pinion attached to its rod through its bearings, fit a washer to position the escape wheel vertically, and then the escape wheel. The escape wheel is fixed in place with a radial screw. Then I fit the balance wheel assembly. And finally, I screw in the drive wheel and attached barrel before hanging on a weight. A final fun experiment we can do with this is measure the drop of the weight for each tick. From this I calculated that the escapement is using around 150 microwatts to run. This is actually very inefficient, and to put this into context, Alastair is currently building a clock that requires just 11 microwatts. What's the cause for this order of magnitude difference? I suspect most of it is due to the hairspring, but I'm always interested in other ideas in the comments. Thank you for watching this video. If you enjoyed it, please consider subscribing to our channel, and we'll see you in the next one.